Uh,
Okay, so let's move on with the talk of Raghav Kansal about particle cloud generation with the message passing GANs.
okay. Hi, everyone. Yeah, as Giuliana mentioned, I'll talk about generating simulations at the LHC, and specifically what we're calling particle clouds with this new architecture. So I'll go over just an overview on simulation at the Large Hadron Collider. Sorry. A brief background on generative model, just focusing mostly on GANs, metrics and representation for the data at the LHC. I'll go over our approach, MP-GAN, and hopefully some current application as well, and then just some discussion. But just to start with, I'll start with just motivating why we would want to use machine learning for simulation at the LHC. And the main reason is that currently the simulations are very computationally expensive. So they can take around 40% of the grid CPU resources for CMS and Atlas. And with the high luminosity LHC coming up, where we'll have an exponentially increasing amount of data we're going to collect, we're going to need an order of magnitude more simulations. And we're also going to have improved detectors, which are more complicated and of higher granularity. So it's going to be a real challenge to keep up in terms of our simulations and computational cost. And so perhaps machine learning is a possible solution to this challenge. And before I go into how we could incorporate it, I'll just go over very broadly how simulations at the LHC work with a bias towards my experiment, CMS. So we start with simulating the hard process, so the main interaction we care about, like two tops being produced or the Higgs. We shower the QCD, like the quarks and gluons radiating, and we get them hadronized into the more stable particles, which we eventually see, like pions, and model underlying interaction in the event. And this gives us this set of generator level particles, which we then traverse through the detectors with something like GAN to model the interaction with the detector materials and the depositions along the detector. We then model detector effects like digitization to get reconstructed hits. And then we do some kind of reconstruction to go from the hits to our idea of what kind of particles produce the hits. In CMS, this is called particle flow. And then finally, we extract or derive high-level event-level variables such as jet PT or missing energy to actually perform an analysis and try to do a search. And so there's an opportunity to incorporate machine learning in many of these steps or all of them. So we could use it to just model the generator level process. We could go from the gen level particles to like the reconstructed hits we get. We could just go directly from gen level to reconstructed particles. So basically modeling the detector interaction with particles, or we could go really wild and just model the full thing end to end. And basically the idea is we're trading the accuracy we would get of doing this full simulation with Pythia, GAN, particle flow, and so forth for perhaps getting a significant speed up. So we probably won't be as accurate if we use machine learning, but if we're fast enough or significantly fast enough, then it might still be a benefit. And then we're also trading our trust or verifiability in this process by skipping a number of steps. So, if we went all the way to high level features directly, that'll be really fast, but would we really be able to trust that we're modeling those correctly? That's a very difficult question when we do a full end-to-end kind of thing. Okay, so I'll try to touch on these things a bit, but I'll also just define this problem in the statistical or machine learning sense very quickly, which is that we want to model our underlying data distribution, where our data can be any of these data, depending on where we want what we want to target. And this is a rich area in machine learning of deep generative models, where we use deep neural networks because they're typically quite flexible and expressive, and typically we parameterize our model with high capacity deep neural networks. Okay, so I'll probably skip just this intro slide. So on different types of generative models, and maybe we can have a longer discussion afterwards. But broadly, we can do this kind of direct modeling, an example of which Uros mentioned, which is flow-based, where we basically try to get an explicit specification for our data distribution. But I'll talk about the models we're using, which are a type of latent variable model. Now, my slides are on Indico if you want to take a look at that afterwards. Where latent variable models are, we basically assume this high dimensional data can be modeled by a lower dimensional, hidden space, like features Z. And the generative process is basically sampling from the simpler prior, and learning the conditional distribution of X given Z. And so one type of network which does this, or architecture, is a variational autoencoder, which has been discussed. But the network we chose, or the architecture, are generative adversarial networks. So these are actually kind of abandoning the likelihood-based loss approach from all the previous models that I mentioned or I showed. And instead of trying to optimize the log likelihood directly, we're basically using another network called a discriminator as our loss. So the discriminator takes samples from our generator, which is trying to take these latent variables or just noise to produce a realistic looking sample, and tries to discriminate between the real and the fake samples. So essentially, this is forming a feedback loop where both networks are trying to improve each other iteratively and adversarially until if it's trained correctly and well, the generator should be producing realistic looking samples that the discriminator can't distinguish between. And so, the GANs tend to be quite hard to train because there's an adversarial process, and it's hard to find a stable point between them, and we lose access to the likelihood. But when they're trained correctly, they tend to be the most performant, at least in computer vision tasks, like or generating images and so forth. Or at least this was the case until last year, where score-based diffusion models actually started beating GANs for the first time. So I don't have time in this talk, but again, it's a very interesting direction which we can discuss afterwards. But I'll move on to maybe a more important question than just the type of model we want to use, which is, once we have this simulated data, how can we trust this to use in an analysis? And kind of relatedly, how do we compare between all these different generative models, which are basically doing the same task? How do we choose which one to use in CMS or whatever? And so the answer to both of these are to develop, very thoughtful and thought out evaluation metrics. So we want metrics which are sensitive to the quality of the data we produce, the diversity. So are we actually capturing the full distribution, and ultimately the physics performance? So they should be interpretable and give us a handle on whether we can use these in an analysis at the end. And then on the more practical side, we want to make sure these metrics are standardized across at least a collaboration, if not the field. And that they're reproducible. So if we apply them again the next day, they should give us the same value, and that they're fast. All right. And so arguably it's the most important aspect really of this kind of generative modeling. And I'll discuss two key metrics which we propose. So one is a more physics inspired metric called where we measure the one-Wasserstein distance between physical feature distributions. And the second is more from the machine learning side, which is adapt this established metric from computer vision to our task. So I'll go over both of these in more detail. And we practically found that together these satisfy our criteria very effectively. And in an effort to standardize these across high energy physics, we release these and more in this open source Python package. So I'll go over the first metric, which basically the traditional method for evaluating these simulations outside of machine learning as well is to compare physical feature distributions. So even for Monte Carlo generators, for CMS FastSim and machine learning applications, we just look at physical feature distributions across all our samples. And we're basically proposing to quantify this using the Earth movers distance, or the one-Wasserstein distance, which is the work you have to do to transform one distribution to another. And through this, we can evaluate multiple features, low and high level, so it's very sensitive to the quality. It's the Wasserstein distance is also sensitive to diversity. It'll give high scores if you're missing, if the supports of the distribution are different. It's fast, reproducible, it's interpretable because we know what features we're evaluating. We can also use bootstrapping to evaluate, to compare just sets of real samples with each other to have a baseline score to compare our generated samples with. But some drawbacks are that it's hard to scale to higher dimensions because the Wasserstein distance is very slow. You're missing correlations between features in that case, and it's not clear how we would aggregate scores across the different features if we're doing them individually. So these two problems are solved if we look at the a metric for machine learning, which is basically we use, instead of physical features, we use features derived from a pre-trained classifier instead. So the example which we showed is applying this to jet generation, where we use a pre-trained graph classifier for jets, which has been very popular in high energy physics, called ParticleNet, where we have our input graph and we do a bunch of graph neural networking and fully connected networks at the end to derive a label. And we feed in the real and generated jets, and we take the activation from the penultimate layer. We fit Gaussians to them and measure the Fréchet distance between them. And so the idea is that a high performing classifier is learning the salient features from our data, just like our hand engineered features would. And it means that we retain the sensitivity to the quality and diversity we get from these individual features. It's fast and reproducible. And plus it's a single aggregate score across all these features, measuring the correlations, and it's easy to scale up to higher dimensions. But we lose the interpretability with this because we don't really know what features it's looking at directly. So that's why we advocate for using it in conjunction with one Wasserstein scores. Okay. Some alternatives I'll go over quickly is, why Wasserstein instead of like Kale, Jensen Shannon, or chi-squared, especially chi-squared, which is ubiquitous for doing goodness of fits. The main reason is that while it's good for like an analysis, for generative modeling, we want the metric which takes into account like the metric space. So Kale, Jensen Shannon, and chi-squared are all F divergences, and which don't take into account the space. So just a quick illustration is that if we have this real distribution and we have two generative models producing this and something like this, the F divergences will all give the same score, which is reasonable for a goodness of fit, because neither of these are getting it right. But for generative modeling, we would want to know that the second model is closer to the real distribution than the first. Okay, there's also this classifier metric proposed, for example, in this Callow challenge we have, and in a number of works. So this has a lot of benefits where we're basically training a classifier directly on the real and generated samples and seeing how well it does. So we end up with a good measure of the quality and the diversity, because if you're only producing a subset of the samples, the classifier will be able to just detect those directly. But the reason we're not advocating it for using our collaboration is that it's not very reproducible or fast, because you have to retrain a classifier each time, and it's hard to standardize people training a classifier again, across the collaboration. And so yeah, that's why we're sticking to the first two. All right, yeah, that was a brief overview of the metrics, and I'll now move on to how we actually represent the data for our model. So this is an interesting problem where we can try to think about how to incorporate inductive biases into existing machine learning architectures. So our data tends to be, well, I'll go over some properties of our typical LHC data. So these are two typical examples of data we see, which are hits in a detector and particles in an event. And so they tend to be quite sparse, highly granular, with an irregular underlying geometry. So what we could still do is try to transform these into an image-based representation. So convert this detector and regularize it, regularize like these little cells into pixels in an image, or the particles in this momentum space as an image. Mostly so that we can use existing architectures which have worked really well, like convolutional neural networks. But again, we can see that the representations we end up with are quite sparse, and we kind of lose some of the irregular geometry we can have in our detector if we regularize it. A more efficient representation could be to just take the features of the hits or the particles and store them in a list, like the energy and the coordinates of the hits or the particle momentum. But there we're imposing an ordering on our particles or hits where there really is none in the underlying data. So instead, what we and a lot of people are using is a point cloud based representation where we store only the hits and the particles. We retain full feature precision. We don't lose any granularity. It works for any underlying geometry. And it's just a set of points in space. So there's no ordering. So it's a natural representation for this type of data. So we can take the hits and their features, or the particle and their features, and store them in this point cloud in position or momentum space. And so this representation is more physics motivated. It captures the underlying geometry. It respects some of the symmetries in our data. And using this along with what are called graph neural networks, which exploit the geometrical information and inter-hit node correlations, are state of the art in our experiment. So some examples are ParticleNet for tagging jets, which has allowed us to do analyses we wouldn't really have thought of doing just a few years ago, like measuring the Higgs to core couplings, and ML for particle flow. So doing the reconstruction step, again, using graph networks, so going from hits to reconstructed particles. And so our idea is to basically extend this to generative modeling. Okay, so I think in the interest of time, I'll have to skip over some of the current applications to just give context. So again, we can discuss these more, but basically there's lots of work in this area, like Atlas FastCalloGAN, or yeah, these sparse approaches. So these are going directly from basically an end-to-end to directly to the high-level features. And so a lot of these approaches are successful, but they're image-based. And so again, it's difficult to see how to scale it to high luminosity LHC, where we have very high granularity calorimeters coming up, like the named high granularity calorimeter in CMS. And so we develop a graph-based approach where the key ideas are that we're taking this natural, sparse, and flexible representation for our data. And we want to learn the global features and interparticle correlations in our data sample. So like the jet structure and the shower structure. Okay, so I'll walk through the architecture. So we develop basically a GAN where we use a message passing network for the generator and the discriminator. And so how that works is that the generator starts with a point cloud of just noise as all its initial features, labeled as so. And one iteration of message passing means each node in this point cloud receives information from all its neighbors, transformed through some learned function, which we implement through neural networks. And then all these messages are aggregated and used to update the node's features, again, through a learned function with a neural network. And so this is done in parallel for all the nodes in a graph, however many times, until we output a hopefully realistic looking particle cloud with our desired features. And the discriminator takes a real or a generated particle cloud, again, goes through message passing with some intermediate graph, and this is aggregated and fed into another network to say whether it thinks it's real or fake. All right. You mean the initial particles or the? So this message passing step is deciding that, because the where they are is a feature. So the node, the momentum, and the angular coordinates. So we can basically have a max. The max is fixed, but under that, implementation wise, we can have any number of particles under that. We have to fix a max just for the GPU have a limit on our batch size. But apart from that, yeah, it's flexible to the number of particles. Okay. So I'll talk about our data set next. So it's yeah, so it's using Pythia simulated high momentum jets. We take the 30 highest momentum particles with their angular coordinate and momentum features, store them in a particle cloud. This is going from basically a gen level particle to a reconstructed particles and a reconstructed jet. And we're taking gluon, light quark, and top quark jets and taking their final jet constituents as our target. And so the results, first, I'll just show on gluon jets, where we can first look visually at some distributions. So the particle momentum, the jet mass, a jet energy flow polynomial, which is basically measuring the particle correlations. And so we can see visually that the real distribution in red matches really well, or our generated distribution with MP-GAN in blue matches really well with the real distribution. And we also compare with some existing point cloud models from computer vision in green and brown. And we see both qualitatively and quantitatively on the metrics I mentioned that MP-GAN performs the best. It significantly outperforms on the high level features, which are these global features like the jet mass, energy flow polynomials, and the Frichet particle net distance. And as I mentioned, we can use bootstrapping and get a baseline score of just real versus real W1 scores. And we can see that the mass and EFP scores are within error of the real versus real baseline. So that's a very good sign that we're learning the jet substructure correctly, and it's hard to do much better than this. Okay. Top quark jets, which are more complicated because we have a top quark which decays into a W boson and a B quark, which then decays into two more jets. So it's a very complex jet, and we also have clustering effects. So sometimes when we try to cluster this afterwards, we miss one of the B jets. So we end up with just a W mass at a lower mass peak compared to the actual top quark mass. So it's a lot of complex physics and effects happening here, but we can see visually that MP-GAN is able to learn this bimodal distribution perfectly as well. Also quantitatively, we see that the mass and EFP scores remain within error of the real versus real baseline. Okay. Yeah, so it's not able to deal with the zero padded particles in the input. So it's really susceptible to having, we have to zero pad it to have a fixed graph as an input. So our approach, it's like a technical detail that we use masking. So basically the zero padded particles have no effect on the model. But if graphs inherently don't need any zero padding because they can be variable sized. So, but graph CNN specifically does need to have a fix, that their model specifically needs a fixed size. Yeah. All right, so just to summarize, our model, this graph-based approach is very successful at learning the complex physics substructure. This discriminator, which is very annoying to train with, GANs in general, very annoying to train, but we find that having this graph-based discriminator loss is actually very crucial to learn the particle correlation. So we can see in ablation studies and a bit in the previous slides as well, that we need a discriminator which looks at the full correlations and is able to learn the jet mass and these kinds of high-level features to tell the generator to learn them as well. Right, and so the goal with this is basically extend this to actual calorimeter simulation at the LHC. So basically going from gen particles to reconstructed hits, that's where we think we could have the highest impact in terms of the accuracy versus speed trade-off. And so the next steps in that regard are to use to extend this to conditional generation and metrics. So basically learning this conditional distribution. So condition on like an electron with a particular form momentum and trying to get that shower, scaling to larger point clouds, and development and application to real CMS data sets. Okay, thank you.
Thanks for the talk. Question there.
What is the sort of future outlook thing? Because is the intention to eventually?
It's a little muffled.
Oh yeah, I'll take this off. What did you?
Oh, okay. You gave some reasons why you didn't like the classifier metric, but I'm curious. It's still the sort of the most sensitive metric in principle to the quality of the generative model. So I'm curious if you guys have tried testing it out on your MP GAN,
Yeah.
and if so, what did you get? What did you find?
It's like it's a little difficult to compare the absolute value, but for example, we got an accuracy of 70% on the network. But I agree in theory, it is the most sensitive metric you could get, but you would have to tune the classifier, right, to get that. And so it's a little dependent on, it's like we're measuring both the generative quality, but also our metric itself, like how well we train the classifier.
But just so you trained a classifier on the low level information, you use ParticleNet on the generated particles. You got 70%. That's great. Yeah. Okay.
Thank you.
Well, I mean, in my experience, every GAN I've ever looked at, it was always 100% separable from the reference data set. So to get less than 100% is, I think, a victory. Yeah.
I'll take it.
So what's the outlook for this kind of fast theme thing? Because for theorists, I guess the gen to Rico particle aspect of it would be very useful. So is there any intention to release this more publicly for use of more than just CMS?
Yeah, so all this work is public. So
fantastic.
Yeah, it was the physical chemistry workshop years ago and conference last year, and all the code and everything is public. For the CMS, the stuff which we train on CMS data specifically is up to the collaboration to decide whether it can be released. I would love for it to be published, but there's a lot of politics there. Yeah, but otherwise there's no reason why it shouldn't be public.
Thanks. I have is there bursts for like detector unfolding?
To go from Rico particles to GAN particles. I mean, not this project specifically. Like GANs can be inverted, for example. So it's we could, in theory, do that. Train a network to do Rico to GAN particles. Yeah, we could do that. I don't know if anybody's looking at that yet. So that would be useful, I guess, for theory as well, to look at our output data.
I mean, because right now some analysis is much less. I guess this would be a better and faster way to do it, no?
Yeah, that's
say TT bus spin correlation, they give the results, unfolded results. At least I know Atlas does. I don't know about CMS.
Okay. Yeah, I would have to think about the actual application, because in principle we have the truth information already from our simulations, but yeah, we could do that for data. Yeah, that could be an interesting application as well.
Thank you.
Thank you.
Additional questions? Okay, if not, let's thank the speaker again.